Welcome back, everybody. We are talking about solutions today. Now, we are still on the journey of characterization of matter. Why? Because chemistry, by definition, is a science of characterization of matter. And by matter, we mean stuff stuff around you, including you. So we are still studying characterization and properties of this matter. Now, the other part of chemistry is studying the changes that matter goes through and the energy that is involved. But we will talk about that later. So far, we're still on the characterization of matter. Now, we have spent a lot of time looking at the tiny things that matter is made of. What are those? Atoms, right? Atoms, elements. And then we went further. We learned how these atoms and elements combine together to make what? Compounds, right? We learned how we make compounds, and we spent so much time learning about the structure, the electrons, the different polarities. We spend a lot of time studying what happens at a small scale. Why? Because as we hinted last time, what happens at small scale governs what we see at a large scale. Meaning that the fact that water is polar is what makes it dissolve other things, right? It's what makes it crucial for life, to be honest, right? So small things, just the geometry, the structure of electrons, the fact that we have 3 versus 5 valence electrons, all of that is what makes matter behave the way it does. But today we're zooming out, we're looking at big, big solutions, right? So if I make like like a lemonade, right? Or coffee, how are the chemicals going to mix? If I add oil in my lemonade, is the oil going to dissolve? Probably not, right? What about sand? Is sand going to dissolve? Probably not, right? But what about salt? Salt is going to dissolve. But why? So why? Why? Sand is a chemical. Sand is SiO2 and salt is NaCl. So why will one dissolve and the other one not dissolve? And that is chemistry, right? So we are going to talk about solutions, and I'm going to introduce an important concept of concentration. And unfortunately or fortunately, depending on who is watching, we are going to do some calculations. But I'll make sure that I explain it, I'll make sure that you understand it, and I'll make sure that I give you some practice, I give you some questions to do on your own, and I will leave it up to you to come to me with any questions that you have. So without further ado, let's get started. All right, so we're talking about physical properties of solutions. So first of all, what is a solution? When we talk about a solution is a homogeneous homogeneous mixture of two or more substances. Homogeneous mixture. And I want everybody to understand this. Why? Because let me ask you this, right? And you might have seen this in high school. Some of you might have seen it, some of you might have not. But what's the difference between a homogeneous and a heterogeneous mixture? What do you think? Like, think about it, right? What's the difference between homogeneous and heterogeneous mixture? Is this lemonade a homogeneous or heterogeneous mixture? And it is a homogeneous mixture. Why is it a homogeneous mixture? This is a mixture in which you cannot see the components, right? You cannot tell me in this exactly where water H2O is, or exactly where, I don't know, sugar is, and what did they put in the lemonade? I guess lemon. So you cannot tell me where each one is. Why? Because it's a homogeneous mixture. That is a solution. A solution is a homogeneous mixture of two or more components. Very important distinction, very important thing to remember, right? And then a heterogeneous mixture is one where you can tell. Right? Can you think of one? I can think of one. Like, let's say you take a mixture of M&Ms, right, with different colors. Can you tell which one is which? If you can tell which one is which, it is a heterogeneous mixture. A famous example is rocks, right? Sometimes you can see rocks with different layers. So it's a mixture, but it's a mixture where you can tell which rock is which, right? So a solution is a homogeneous mixture of two or more, right? So one of my favorite thing is to ask, like, hey, is this a solution or not, right? Where did my thing go? Where my PowerPoint went. Oh, there you go. Okay, we're back. All right, so a solution is a homogeneous mixture. Now, what is a solution made of? A solution is made of a solute and solvent. Solution is made of a solute and solvent. What is a solute? A solute is the one that is smaller. A solvent is the one that's bigger. It's that simple. I'm mentioning it because I like to ask questions like, I give you a solution and ask you what is the solute, what is the solvent, and a lot of people think about it too much, but no, it's like the one that's small is solute, the one that's big is solvent. If I take water and add a spoon of salt, is that a solution? Yes or no? A solution because it mixes, right? And then if I do that, what is the solute? Is it salt or water? The solute is salt because salt is the one that is small. Water will be the solvent. And what if I take the same cup and then I'd add sand? Is sand okay? Is sand in water a solution or not? The answer is not, because if you add sand in water, they will not mix. So you will be able to see which one is water, which one is sand. And that, ladies and gentlemen, is not a homogeneous mixture, if you can tell. So it is not a solution. But I gave you some examples here to show you that sometimes it's not so clear, because a solution, I've been talking about liquids, but a solution can be gas as well, right? For example, air is a solution. Why is air a solution? Because a solution is a homogeneous mixture, and air is a mixture of many gases, and we can't see which one is which. Anybody remember what air is made of? Oxygen, right? Oxygen, nitrogen, and other gases. So air is a good example of a solution, right? But sometimes you can mix, right? You can add a gas in the liquid, like in soda, right? In soda, you have CO2. Those bubbles are CO2, right? Or sparkling water, right? You can have a solution like that. Or you can add a gas in a solid, right? You can add a liquid in the liquid. Most of these are liquid in the liquid, but you can add a solid in the liquid, like NaCl in water, right? So you can have different types of solutions, right? Different types of solutions. So I want you to familiarize yourself with solutions. And the first question is, what is the difference between a solute, solvent, and a solution? And I want you to give an example of an item or a solution you use every day. Something that I haven't talked about before in this video, but I want you to give me an example of a solution, and in that solution, give me what is a solution, what is a solute, what is the solvent. This is good practice, right? Now that we know what a solution, solute, and solvent is, let's go into what is a saturated solution, unsaturated, and super saturated, right? I was in a lab today and I was actually working with these types of solutions. And think about it this way, right? We're talking about how you can add a spoon of salt in water, right? In a cup of water. What if I add 2 spoons? That's okay. 3 spoons, that's okay. What about 10 spoons? Oh, now we're getting somewhere, right? Well, what about 20 spoons of water in that cup of, 20 spoons of salt in that cup of water? Too much salt, right? So there's a limit. There's a limit. There is a limit amount a certain solvent can take. A limited amount of salt a certain solvent can take until no longer can dissolve, right? So a saturated solution contains the maximum amount of a solute that will dissolve in a given solvent at a specified temperature, the specific temperature, because if you increase the temperature, the solubility will change. Again, if you increase the same temperature, the solubility will change, and we'll talk about that later. But again, saturated solution is a solution that contains just the maximum amount. An unsaturated solution contains less solute, right? And then look at this. The super saturated solution contains more. It contains more solute than is present in a saturated solution at a specific temperature, right? So a super saturated solution will contain more than is present in a saturated solution. Super saturated, right? So again, what is the difference between a saturated? This is actually question 2, not question 3. But what is the difference? Right? What is the difference between a saturated, unsaturated, and super saturated solution? And I want you to give an example of what we use every day, right? You can use salt, you can use sugar, you can use whatever, but something that we use every day that will give you a super saturated. Right? So this is question 2. All right. All right. So let's look at something else. Let's look at another concept when it comes to solutions, right? Another concept is the interaction, right? Interaction in the solution process. What do I mean by that? The solvent, the solute, the solution, guess what they are? Chemicals, right? They are all chemicals. And guess what? All of these chemicals are going to interact with each other, right? So we have solvent-solvent interaction, right? That already happens. Right, and then you have solute interaction, right? Solute interaction. So the solute itself interacts, the solvent itself interacts, but then you have the solution, right? So delta H, if you remember, this is what we call enthalpy. This has to do with energy. If we are calculating the energy of the solution, we're going to take the energy of the interaction between the solvent molecules, then the energy of the interaction between the solute molecules, and then lastly the energy of the interaction between the solvent and solute, right? That is basically all the interactions that are happening, and as you can imagine, some of these actually produce chemical reactions that we'll be looking at later. But let me introduce you to another concept when it comes to solution. I will say this many times, and you hear this a lot. But this is like dissolves like. Like dissolves like. What does that mean? Very easy. This has to do with if I give you 2 things and I ask you like, hey, will this thing dissolve in water, for example, right? Dissolving means one is a solute, the other one is a solvent, right? So if I say salt dissolves in water, means that salt is a solute that dissolves in water. So if I ask you, will salt dissolve in water? You will look at the polarity. You will look at the polarity. So when we say like dissolves like, we mean that polar things, polar molecules dissolve in polar solvents. And then non-polar molecules are going to dissolve in what? In non-polar solvents, right? And then ionic compounds are very polar, right? Ionic compounds are very polar, so they are usually soluble in polar solvents. Ionic compounds are very polar, even more polar than actual polar molecules, right? So that's why NaCl, which is ionic, dissolves in water. And SiO2, by the way, sand is non-polar. It's non-polar. That's why it doesn't dissolve in water, right? So like dissolves like, you will need to know this. You will need to know this. This will come back many, many times, right? So question number 3 is, right? Question number 3 is, give 2 examples of things that can dissolve in water and 2 examples of things that can dissolve in oil. And then I want you to explain to me what is the difference, right? Oil, to give you a hint, oil is non-polar. Oil is a fatty acid, is non-polar. It's mainly non-polar. So water is polar, extremely polar, as we already seen. Oil is non-polar. So give me 2 things, 2 examples, not just things, chemicals. Chemicals, 2 chemicals that will dissolve in water, and then 2 chemicals that will dissolve in oil. All right, that is question 3. And that should be easy. That should be easy based on what we just discussed. Now, let me introduce you to another concept. And this concept is concentration. You've heard this before. Oh, this water is concentrated. This, this, I guess, coffee is concentrated if you have like a lot of caffeine or something like that. But concentration is one of the most important concepts in chemistry. Why? Because chemistry deals with chemicals, right? And chemicals, the measure of chemicals is concentration. It's just like when it comes to cars, we measure distance in meters, right? We measure distance and we measure speed. So when it comes to chemicals, we measure concentration. So that's how, just like distance is important when it comes to cars and navigation, concentration is important when it comes to chemicals and chemistry. All right, so let's look at this, right? The concentration, right, by definition, is usually the amount of solute present in a given quantity of solvent or solution. Does that make sense? So if you, how do I say this? All right, so we're going to look at like 6 different ways we measure concentration, but all of them are a certain quantity of solute over a certain quantity of either solution or solvent, right? Because again, that's what a solution is, right? Solute in a solvent. So if you have 10, right, 10 grams, right, 10 grams of salt, 10 grams of salt, you added 100 grams of water, right? 10 grams of salt, 100 grams of water, you can measure percent by mass. Percent by mass, we also call it weight by weight. Percentage, right, is going to be equal to mass of solute. So that would be our 10 grams for salt. And then it's going to be over mass of solution. Mass of solution is usually mass of solute, which is 10 grams, times the mass of solvent, which is 100 grams, we said, of water, right? Times 100. So the percent mass of our solution will be 10 grams over 110 grams times 100. That will be the concentration. If I ask you to give me the concentration of percent by mass, okay? Percent by mass, that's the one. So I can give you like, okay, a sample has this much gram of potassium chloride and it is dissolved in this much water. And then I ask you, what is the percent by mass of the solution? And then you're going to say percent by mass or weight by weight is going to be equal to what? It's going to be equal to grams of solute over grams of solution times 100. So what is this? 0.892 grams. That's the solute over grams of solution. Remember, grams of solution is not water. Water is a solvent. So the grams of solution is solute plus solvent. So it's 0.892 grams plus 54.6 grams times 100, right? So this will be the percent by weight by mass. Okay, so let's actually do it. So it's good to get in the habit of doing these with me, by the way, just to make sure that you're doing these calculations right, or that I'm doing it right. So do this with me. Over 0.892 plus 54.6 1.6. So I got 1.6%. That is the weight per weight concentration, right? All right, so I can also oh, never mind. I just I shouldn't have written it. It's right here. But we don't just say weight by weight, right? We also do, check this out. So we do percent by mass, right? Which is mass of the solute over mass of the solution times 100, right? And mass is in grams here. But we also do percent by volume, which is important. This is an important one, right? Percent by volume. So we got weight by weight percent again. We got percent by volume, which is volume per volume, right? And there's another one that's not here, by the way. I want you to write it down. Write this down. There is also weight per volume percent. Weight per volume percent, right? The weight per volume percent is going to be equal to weight, so grams of solute over milliliters of solution. Everybody with me? So we have weight by weight percent or percent by mass, volume by volume percent or percent by volume, but we also have weight per volume percent, right? But then we have these are actually important, right? ppm and ppb. What is ppm? It's parts per million. You might have heard of this, but we do this when we have very, very small particles, right? I don't know if you've noticed this before, but we are going to have different measures of concentration because we will be measuring different things, right? If you're measuring salt in water, you're not going to use the same amount of, like, I don't know how much mercury is in the whole ocean. That will be much lower, right? Just like I don't know, like when we measure height, we use feet and inches, right? But when we measure distance traveled, we use like miles, right? That is the same thing. We are using different concentration calculations because we measure different concentrations based on what we have, right? So ppm, or parts per million, is going to be mass of solute over mass of solution. That's okay, but instead of multiply by 100, we multiply by a million here. That's why we call it parts per million, right? So it's kind of like weight by weight or percent by mass, right? But instead of being based on percentage, it's based on million, right? Parts per million. And parts per billion Same thing, but multiplied by a billion. There's actually a PPT, which is parts per thousand as well, right? So these are, I want you to write these down. I want you to write these down. These are the first part, the first layer of concentration, right? The first layer of concentrations. And let's see if I have a question for you. No, not this one. We're not there yet. Where is it? Okay, yes. So this question 4, we're gonna make this question 4. Okay. So sulfuric acid, right? Sulfuric acid is 98% by mass. Oh no, actually we're not there yet. Never mind. Sorry, let's not make this question 4. I don't have question 4 then. That's okay. Okay, let's actually do our own question 4. Because I want you to get a chance to practice all of this, right? So I don't want to skip a step. So let's do this. Let's do this. Okay. Let's say a solution is made. So Q4, a solution is a solution of KCl has a concentration of 15% weight per volume percent, right? Weight per volume percent, right? This is weight per volume, right? And a volume of 895 milliliters. What is the mass of KCl, right? That is the question. Now remember, weight per volume percent is equal to grams of solute over grams of solution times 100, right? You can use this to find the grams of KCl, which are they grams of solute, grams of solution? I don't know. You tell me. But that should be a good hint. But let's go to the next set of concentrations, because we are not done with concentrations. These are my favorites, right? Molarity and molality. These we use way more than the ones that we just discussed, right? Why? Because these are based on moles. They are based on moles instead of just grams, right? They are based on moles, and we measure chemicals based on moles. A mole is a better indicator, right? So molality we use all the time. I probably use this every day. I use this today. I used it yesterday. I'll probably use it tomorrow, right? Molarity, we use it as scientists every day because it's very easy to deal with compared to everything else. So, and I want you to know how to calculate this, right? So it's going to be moles per liter, right? I like to write it down like this: N is moles over volume in liters, right? So my abbreviated formula is M is equal to N over V in liters. Why? Because again, N in moles is in moles. So how do you find moles? Like if I give you grams, how do you find moles? If you can answer this question and you remember it, it will give you a lot of points for the rest of the semester. Promise you that, right? Because we're gonna be going to moles and grams and back. Now I'm gonna give you a quick formula that I use, which is N is equal to M over molecular weight, right? So N, which is moles, is equal to the mass in grams over molecular weight. If you can memorize this formula, that's okay. But if not, then you can convert it using dimensional analysis, like you learned in the last class. But everybody needs to know how to go from moles to grams, grams to moles, because we're gonna need moles in calculating the molarity and the molality, right? The only difference is we're going to take moles over the liters of the solution in molarity, and then in molality, we're going to do moles over kilograms. So it's going to be N over kilograms of solution, right? Molality is equal to N, which is moles over kilograms of solvent, actually, right? That's another thing to keep in mind, right? Kilograms of solvent, whereas here it's liters of the solution. So that's molality and molarity, right? Very important, very, very important, right? So let's say I ask you like, hey, what is the molality, right, of this is actually a good question. I like this, right? Because it gives you M. That's another thing, by the way. It's very important to remember, right? If you have for the molality is M, right? It's small m. So if I have like something that has a molarity of 10, I say 10m. For the molarity, which we're gonna use way more, it's big M. So if something has a molarity of 2, we say 2m or 2 molar, right? So here I have 5.86 molar of ethanol, right? And then I have density, and then I ask you what is the molality. This is a fun one. This is a fun one because it kind of requires you to know what's going on, right? Because if you remember, the molality is moles of solute over mass of solvent, right? And check this out, right? And this is kind of, I like this question. I like this question because it helps us understand this. Because molarity, right? If I say 1 molar or molarity, from the formula, what is molarity? Is moles per liter. Moles per liter, right? Moles per liter. So if I tell you that something is 5.86 molar, or with the big M, I'm telling you that 5.6, so it has 5.6 moles of ethanol in 1 liter of solution, right? 5.6 moles in 1 liter of solution. So if we have 1 liter of solution here, right, we can convert this, right? We can convert this moles into grams, right? Because we have the molecular weight of ethanol, right? Everybody with me so far? And then what is the grams of solution? The grams of solution, we're going to get it from the volume of solution. That's why they gave us the density, right? Let me put it here because I can see that even though this is a video, I can see that someone on the other side might be confused. Not you, but someone might be confused. So let's see if we can start over here. All right, so what is the molarity of this, right? So they gave me the molality. So molarity, right? The molarity they gave me, and it is 5.86 molar, right? And the information that this gives me is 5.86 moles per liter. Why? It's because molarity, or M, is moles over liters, right? So M literally tells us that these many moles are in 1 liter. All right, that's crucial information, right? Because then they are giving us that you have 5.86 moles of our solute, right? Ethanol of our solute. And then they're giving us liters of what? If you remember correctly from our formula is liters of solution, right? So 1 liter of solution. So that means that you have moles of solute, then you have volume of solution. That's okay, you're good. But the problem is they're asking for molality, which is equal to moles, right, of solute, which you have here. That's great, but it's over not volume but kilograms, and it's not kilograms of solution, it's kilograms of solvent. That's the problem, right? So we already have the moles of solute, no problem, we're gonna use it. But this 1 liter of solution, we need to find the kilograms of solvent, right? So 1 liter of solution, we need to find, okay, kilograms of solvent. So the first thing we're going to do is, okay, we are going to be like, okay, we're going to convert this 1 liter of solution into kilogram, because again, we need kilograms, right? So at the bottom here, we want to have kilograms of solution. So this is the density. They gave us a density so that we can convert it. So they converted 1 liter, right, times that. So 1 liter times this density, right? So it's this gram per milliliter. So this will be 927 grams, right? Or just 0.927 kilograms, right? So we just went from here to here, solution, right? That's okay, that's good. So we're making progress, but down here we cannot use solution, we have to use solvent. So how do we get kilograms of solvent if we have kilograms of solution? Well, if you remember, solution is equal to solvent plus what? Plus solute, right? So kilograms of solvent here will be equal to kilograms of solution minus kilograms of solute. You with me? That's how we get kilograms of solvent. So here, the moles of solute need to go into kilograms of solvent. So how do we go from moles to mass? Do you remember, how do we go from moles to mass? We use the molecular weight, right? If you remember that little equation, we're going to use the molecular weight. And I gave you a little equation that says that moles is equal to mass over molecular weight. So mass is equal to moles times the molecular weight, right? So we have the moles here. Then we can find the molecular weight of ethanol because we have the formula, right? The molecular weight, in fact, is 24 plus 5 is 29, 29, 30, 30, 8, 38. It's probably 38 grams per mole, right? So you take the molecular weight, multiply by the moles, that will give you the grams. That will give you the grams, right? So what they did here, they took that and it's 0.27 grams, right? 0.27 grams, right? This is the kilograms of solute. This is kilograms of solution. So how do we get kilograms of solvent? We're going to get kilograms of solvent by taking kilograms of solution, 0.927 kg, minus the kilograms of solute, which is 0.27 kg, right? Kilograms. And then at the top, we have the moles of solute, which they gave us here, right? 5.86 moles of solute. And that will be your molality, right? Now, this is kind of more of an advanced question, but it kind of puts into perspective everything so that you understand it, right? So I really like this question, but if you don't understand it, that's okay. Just take time to understand all these terms. Good thing this is a video, so you can like rewind it, go back, try to understand, and you also have access to these slides as well. Now, let's do something easy, right? Let's do something easy. So calculate the molarity of sulfuric acid containing this many grams in this many grams of water. All right, so this one, we're asking for molality, right? If you remember, molarity is equal to moles over volume in liters, right? So do we have the moles? No, we don't. But guess what? We have the grams and the molecular weight. So moles is equal to the mass over molecular weight, if you remember. So do we have the volume? We don't have the volume in liters, but guess what? We have the grams of water. And water, the beauty of this is water, the density of water is 1, if you haven't heard this before. So 1 kilogram of water is equal to 1 liter of water. 1 gram of water is equal to 1 milliliter of water. It's pretty cool. It's pretty cool. It's unbelievable, but it's true. So that means that here you have 198 milliliters of water, right? So that means that the volume, we already have the volume, and the volume has to be in liters, right? So the N, we gotta find the N first, which is the mass. The mass is 24.4 grams of sulfuric acid over the molecular weight, which is 98.09 grams per mole, right? And then we gotta calculate that. So it is 24.4 over 98.09. So it's equal to 0.248 moles. All right. And then the molarity, right? The molarity is equal to moles per volume, which is 0.248 moles over volume, which is 0.198 liters. So again, the volume has to be in liters. When it comes to molarity, the volume has to always be in liters. So this is equal to 1.256 molar, right? Molarity is expressed in molar. All right. Let me see if I have another example. Oh, okay. So now, guys, and I'm pretty sure that everybody can do this. I'm pretty sure that you can do this. But when it comes to these chapters, when it comes to this chapter, and the next chapters, when I give you a formula, and I say that molarity is equal to moles over volume in liters, it doesn't mean that I will always give you a question to be like, oh, what is the molarity? Sometimes I can give you the molarity and then I can ask you for something else, right? So for the previous question, right, they gave us grams, and then they're like, okay, find a molarity. But guess what? They can give us molarity and then they can ask us grams, and we should be able to do that, right? So they're asking how many grams of sodium sulfate are needed to make 150 milliliter of a 1.65 molar, right? So what do we have? We have volume, right, which is 750 milliliters. And again, when it comes to molarity, you turn this into liters, so 0.75 liters, right? Then you have the molarity, M, which is 1.65 molar. All right. And then what else do we have? How many grams? They're asking for mass, right? What's the mass? Now, if you remember correctly, right, you have molarity and volume. The formula for molarity is equal to moles over volume. So look at this. If you have molarity and you have volume, what can you calculate here? That's right, you can calculate the moles, right? So you can be like moles is equal to molarity times volume. So what can the moles give us since they have grams? Well, we can go from moles to grams. If you remember, like I said, this equation is going to come back a lot. Moles is equal to mass over molecular weight, right? So then look at this. The mass after you found the moles is going to be equal to the moles times the molecular weight. All right, so we gotta know how to turn these formulas around, not just plug and play. Everybody with me? So molarity is equal to moles over volume, but this gives us the moles is equal to molarity times volume. And then you do that. So go ahead and do that in your calculator, right? Find the moles, which is the molarity times volume. You have the molarity here, you have the volume, you get the moles. Guess what? Since the moles equal to the mass over molecular weight, we can find the mass by taking the moles times the molecular weight. So you get the moles here times the molecular weight of sodium sulfate. What is the molecular weight of sodium sulfate, by the way? Take this as an exercise. Take this as an exercise and double check your math. Like, go ahead and calculate the molecular weight of sodium sulfate using a periodic table, and then after that, Google it to make sure that you got it, because I need you to practice how to get the right number of the molecular weight, right? If you can see, this one is easy. You have two sodium atoms, one sulfur atom, and 4 oxygen atoms. So make sure that you multiply and add them up correctly, right? And then after that, double check your answer. All right. So this is the next question. The next question is, this is question 4. No, this is question 5. We already made our question 4, remember? So question 5 is, what is the molarity of a potassium nitrate solution that is prepared by dissolving 28 grams of potassium nitrate in enough water to make 250 ml? This is easy. This one is easy. We just did something like this. So make sure that you give me a good molarity, right? Now, the next question, question 6, is sulfuric acid is 98% by mass, meaning weight by weight. Then calculate the molarity. Ooh, I like this. Calculate the molarity and the molarity of the acid solution. And then this is the density of the solution. This is a good one. This is a very good one. And the easiest way to remember is, I want to give you a hint because this is a fun one, but the easiest way to remember this is the formulas, right? Percent weight by weight. This is how I call the percent by mass, right? Is equal to grams of solute over grams of what? Of solution, right? So if it tells me that it's 98%, what is it telling me? It's telling me that you have, when you have 98 grams of solute, you have 100 grams of solution, because okay, this is times 100. Almost forgot. It's grams of solute over grams of solution times 100, right? So if it's 98%, it's telling me that you have 98 grams of solute in 100 grams of solution, right? That's it. That's all you need to know. That's all you need. That's all the hint you need, right? Because then now I just gave you the grams. I just gave you the grams of solution as well. And guess what? The density of the solution is going to give you the volume of the solution, and that should be easy to calculate the molarity and the molality. So this is going to be a fun one, but as long as you pay attention to good notes, you should be good. Okay. All right. Okay, so I'm gonna teach you one more thing about concentration before we go on to something else, right? So, and this is a concept that is also very important, man. It's very important when it comes to doing things in the lab, and this is called dilution, right? Wanting to dilute one thing into another. And we do this. If you cook, you dilute things all the time. If you make coffee, you like, we do dilutions all the time. And dilution, as you can imagine, is, when you add more solvent into a solution, becomes more dilute. If you add more solute into a solution, it becomes more concentrated. Right? So dilution is an important concept, because in chemistry we're going to be dealing with different concentrations, right? So let's say you have an acid that's very concentrated, right? It's like an acid is like 12 molar, very dangerous, right? And then we want to make it like 2 molar, less dangerous. Still not good for you, but less dangerous. And we want to make 500 milliliters of this. And I asked you, you were in my lab, how much of the 12 molar will I take and add to water to make 2 molar, to make 500 of 2 molar. That is dilution. Well, it's the easiest formula in all of this, at least I think, because what you're going to do is you're going to say this is the concentration we started with. We call it concentration 1. This is the final concentration. It's concentration 2. This is the final volume, volume 2, and then this is the volume that we would take here is volume 1. That's what we're looking for. So how do we find it? You should remember this, like for the rest for the rest of your life, at least for the rest of this class, right? C1V1 is equal to C2V2. This is the dilution formula. The first concentration times the first volume is equal to the second concentration times the second volume. Because look at this. If we want to find V1 here, it will be C2V2 over C1. So if we want to find how much of the 12 molar we're going to take, we're going to do C2, which is 2 molar, times V2, which is 500 milliliters, over C1, which is 12 molar, right? So we're going to then take 2 times 100, which is 1,000, times 500, which is 1,000. Okay. So it's 1,000 over 12, which is going to be 83.34 milliliter, right? So then, that's V1, meaning that you would take 83.34 milliliter of the 12 molar, and then you're going to add enough water to make it 500 milliliters, and that concentration, the concentration of that would be 2 molar. All right, so that is dilution. It's an important concept, and I put it in here so that you understand it. So this is question 7. Question 7 is a students need to use 0.445 moles of NaOH in a chemical reaction. So that's their volume they want to make. The stock solution is 3 molar. And then how many milliliters of the stock solution are needed to have the proper number of moles of NaOH, right? So to have the proper number of moles. Oh, this is actually good. This is actually good. Okay, yeah. So realize this, right? Because this is this can be tricky, but it's not that tricky, right? So C1 V1 equals C2 V2, right? But if you remember, molarity is equal to moles over volume, right? Remember that, right? What does that mean? Moles, right, or N is equal to M times V, right? What does that mean then? If your concentration is molarity, molarity times volume is equal to moles. And here, molarity times volume is equal to moles, right? By the way, this is why C1V1 equals C2V2 is because no matter how much you dilute, the moles you start with should be equal to the moles you end up with, right? So this kind of explains why we use C1V1 equals C2V2, because the moles are equal, right? So here, again, giving you a hint for these questions, right? If they say you need to use this many moles, it's telling you that C2V2, which is moles, they're already giving it to you, right? And then stock solution is 3 molar, so you have to figure out, is it C1, is it V1, and then how many milliliters of NaOH stock solution. You gotta find that, right? But that is enough hints. All right, so that is dilution, right? So let me switch a little bit about from concentration to solubility, right? So Solubility again is, as I mentioned earlier, how easy something is to dissolve into a solvent. I talked about earlier how one of the biggest things to determine solubility is the nature of the solute and the solvent. And we know that like dissolves like, right? If one is polar, the other one is polar, they will dissolve. But another thing that's important is temperature, guys. So I don't know if you know this. Some of you guys might not have enough experience with cooking, but if you are familiar with cooking or making tea or coffee, you know that in order for something, for sugar, for example, to dissolve faster in your coffee, it needs to be hot, right? If you ever made cold tea or cold coffee and try to add sugar, you know that it takes a while, especially like granular sugar. It takes a while to dissolve, right? So as you increase the temperature, the solubility increases for almost everything. Almost everything. There are some weird stuff that there are some weird salts and chemicals in which solubility decreases with temperature, but for most of the chemicals, solubility is going to increase as you increase the temperature, right? Absolutely. We can take advantage of this. I don't know if you guys know something called fractional crystallization or fractional distillation. But what we do is, if you have a mixture, right? Think about it this way. If you have a mixture of many, many chemicals, right? And you know that they dissolve at different temperatures, right? You can then, right, dissolve your mixture in a sample, right? And then you can cool it down little by little, right? You can cool it down a little bit, and then one solid will cease to be dissolved in that solution, right? So one solid. So think about it this way, right? How do I say this? Okay. Let's say you have water, right? You have water, and then you're going to mix NaCl into water. You mix in sugar, you mix in KCl, you mix in all of that stuff, right? You mix in different chemicals that have different solubilities at different temperatures, right? And as you cool it down, right? As you cool it down, the thing that ceases to be soluble in water at that temperature will become solid. And guess what you do? It's just going to go to the bottom, so you can just collect it. You can just pour out the rest of the mixture. You can collect what's at the bottom, right? Or filter it. And then guess what? You cool it down more. The next one also becomes a powder. Then you remove it, and then you cool it down more. So this is called fractional crystallization. Very advanced technique, but it takes advantage of differences in solubility. There's another thing that we call fractional distillation that does it the opposite way, right? If you have a mixture, you can do a distillation, meaning you can boil it, right? And then as you boil it, you're going to be collecting vapors, right? So they are going to be evaporating at different temperatures, right? So this is called fractional distillation. Very, very common when it comes to industry and also in the lab as well, right? But I won't talk too much about it. Just know that for most of the chemicals, solubility increases with temperature, but there are weird chemicals where when you increase the temperature, solubility decreases, right? And again, this, if somebody asks you why does that happen, has to do with the nature of their chemicals, their structures, their electrons, their geometry, their polarity, and so on and so forth, right? And of course, the nature of the solvent as well, right? So temperature and solubility, very important, right? When it comes to for example, gases, right? For example, O2 gas, its solubility usually decreases with increasing temperature, right? Now, let's talk about more solubility of gases, more about solubility of gases, right? So when it comes to solubility of gases, we have something we call Henry's law, right? And I need everybody to understand this and be able to use this, because Henry's law, right, it tells you that the concentration of a dissolved gas, the concentration of a dissolved gas is going to be proportional or dependent on the pressure, right? So the solubility of a gas is proportional to the pressure. Okay? So concentration is equal to the pressure times a constant, right? A certain number for each gas, right? So this is called Henry's law. But if we want to make it practical, we have to introduce other things as well, right? But make sure that you understand Henry's law. Make sure that you understand what's going on. K is a constant, right? K is a constant, so this will be different for each gas, but it's this is calculated or given. But C is a concentration. This is a pressure, right? All right, so before we do that, let me go to give it a title, right? This is called colligative properties. Colligative properties. Colligative properties, right? So what are colligative properties? The colligative properties, right, are properties that depend on concentration. So these are properties that depend on the number of solute particles in a solution. They don't care about the nature. They just care about the particles. So those are called colligative properties, and I need everybody to know all of the colligative properties and how do we apply them. So let me give you kind of a summary first. A summary is vapor pressure lowering, meaning that when things are dissolved, right, let's say salted dissolved in water, it lowers its vapor pressure. So the first colligative property is vapor pressure lowering. So you notice that the colligative properties are expressed in terms of the effects that they cause. So they are telling you that they lower the vapor pressure. And guess what? They elevate the boiling point. And then freezing point depression, they lower the freezing point, and then they modify osmotic pressure, mostly increasing. They increase the osmotic pressure as well. So there are 4 colligative properties. 4 colligative properties. Remember that, write that down. But we're going to go into a little bit more detail about how to calculate and understand which one of them, starting with vapor pressure lowering, right? So how do we lower vapor pressure? We lower vapor pressure, right, based on moles or molar fraction, right? So this is called Raoult's law, right? Raoult's law, make sure that you know that. So Raoult's law tells me that the pressure, right, the pressure of a certain gas, right, in a mixture, for example, is going to be equal to the fraction, the mole fraction of that gas, right, times the vapor pressure of the pure solvent, or total vapor pressure, right? So if we have, I want everybody to understand this, right? If we have in air, let's say we have nitrogen, N2, and then oxygen, right? Let's say we only have these two. And usually we have way more nitrogen than oxygen. So we have, let's say, 8 moles of nitrogen and then 2 moles of oxygen, right? The total moles will be what? 10 moles, right? 10 moles. So the mole fraction X of N2 will be equal to 8 over 10, right? Which is equal to 0.8. And then the molar fraction of O2 will be 2 over 10, right? Which is 0.2, right? That's how we calculate the mole fraction. And after you calculate the mole fraction, if I ask you, like, give me the partial pressure of oxygen, right? Partial pressure of oxygen, O2, will be the partial pressure, the molar fraction of O2 times the total pressure that we have, right? Or the pure pressure of O2, right? So that is how we use Raoult's law, right? But that's one of the first. So if I ask you, like, hey, calculate the vapor pressure of a solution, right, made by dissolving this much of glucose into this milliliters of water at 30 degrees Celsius, right? So I ask you, like, calculate the vapor pressure and then what is the vapor pressure lowering, right? So we are going to, and they tell us that the vapor pressure of pure water at 30 degrees Celsius is given in that table, right? And we're going to use that, right? So what are we going to do? We're going to use Raoult's law, which is the pressure, the vapor pressure we want, right, is equal to the molar fraction and then the given pressure. The molar fraction, right? So in order to find the molar fraction, you need to find the moles. So in this solution, we have two things, right? We have water and we have glucose. So the moles of water, we can use it because, again, we have the milliliters, right? The milliliters. If you remember, if we have, and I want everybody to practice this because, again, like I said, I will say this many times. How do we get the moles from grams? You use the molecular weight. So here they're using the molecular weight, right? So if you have 460 milliliters of water, if we talked about this, we know that 460 milliliters of water is the same as 460 grams of water. Why? Because the density is 1. So if you have the grams of water, you can get the moles of water, right? And then if you have the grams of glucose, you can get the moles of glucose. So you have the 2 moles, the moles of water, the moles of glucose. And it's the same thing like we did here, the moles of nitrogen versus the moles of oxygen, right? If I got the moles of nitrogen and moles of oxygen, I can find the molar fraction of each, right? So that's what they did here. The molar, after I got the moles, I'm going to get the molar fraction, right? The molar fraction of water is going to be equal to, again, the moles of water over the total, just like we did above, right? So that is the molar fraction. And guess what? The vapor pressure of pure water is already given. So the partial pressure of water is going to be equal to its molar fraction because plus the times the vapor pressure of pure water, right? Does that make sense? So that is the new pressure, right? So if you have, when they ask, like, what is the vapor pressure lowering, they're telling you, like, how much do we lower the vapor pressure, right? If the vapor pressure given, where is my pen? I can't see anything. Okay, it's so tiny. A pen. So if the vapor pressure given is this, and the new vapor pressure we found is this, then what's the vapor pressure lowering? You take one minus the other. Take one minus the other, right? So I want you to notice this, right? Because I don't want anybody to be confused, right? So again, we are measuring colligative properties, and colligative properties are telling us that, hey, if we had something pure, right? If we had something pure and then we add like something pure like water or air or something, and then we add a solute, how does it change things? And we've just seen that it changes the vapor pressure by its smaller fraction. It changes the vapor pressure by a smaller fraction, right? So we can find the molar fraction of pure water, not the molar fraction, but the vapor pressure of pure water. They can give us the vapor pressure of pure water, and then we can calculate how much. So they can give us the vapor pressure of pure water, and then they can calculate how much adding something will change that vapor pressure by using this. Does that make sense? So we can change the vapor pressure by adding something to a pure substance. But then, so if I ask you to calculate the vapor pressure lowering, again, you find the molar fraction times the existing vapor pressure, you get the new vapor pressure. And then you're like, okay, I have the old vapor pressure, I have the new vapor pressure. Did it lower? Yes. I can also ask you by how much. But then let's get to boiling point elevation. So the boiling point goes up. Now let me ask you this, and you might know this, you might not know. But what temperature does the water boil? At what temperature does water boil? 100 degrees Celsius. 100 degrees Celsius. At what temperature does water freeze, by the way? 0 degrees Celsius, right? So that's where these 2 degrees come from. So from this name, you can imagine that the vapor pressure, no, not the vapor pressure, but the boiling point increases, right? So whenever we add something to water or to a liquid, it increases the boiling point. What is the boiling point, if you remember? The boiling point is the temperature at which something is going to boil, right? So water boils at 0 degrees Celsius. Benzene boils at 5.5 degrees Celsius. Ethanol boils at negative, that's pretty low, negative 117.3 Celsius, right? Acetic acid, 60. So you can see that things boil at this low temperature, right? But then I will ask you, like, okay, if we add things into this, right? So no, this is freezing point. This is the freezing temperature. This is the temperature at which they freeze. Okay, that makes sense, because I was gonna say that's very low for boiling. But this is the freezing temperature. This is the boiling temperature, right? But if we add something to any of these numbers will change. By how much? By this formula, right? This formula is called delta TB, for example, right? Delta TB, or the change in boiling temperature, is equal to I times M times KB, right? So what am I talking about? I is called, we call it the Van Hoff factor, and I'll talk about what it is in a minute. M is molality, and then KB is a constant, right? It's a constant that we're gonna use. So each chemical is gonna have its own KB. As you can see, we have different KB, right? So how do we look at this? So if you can look at, see if I can find the Van Hoff factor somewhere. What? Okay, the Van Hoff, right? I have Van Hoff. Okay, so the Van Hoff factor, right, tells us that, okay, we are looking at, with colligative properties, we are really looking not at chemicals themselves, but particles, things dissolved in our solution. So if you have NaCl, we've already learned that NaCl doesn't behave as NaCl in a solution, right? We know that NaCl becomes Na plus Cl minus. So instead of having one thing, one chemical in there, you have two particles. And we care about this because in these formulas, we care about particles way more than we care about individual chemicals, right? So the Van Hoff factors, it tells us the number of particles and really the number of ions if it's ionic, right? So that means that NaCl, look at this, NaCl has how many? 2. I for NaCl is 2, right? I for, I don't know, KCl is 2. I for magnesium chloride, look at this. Magnesium chloride will give us how many ions? It's going to give us 1 magnesium and 2 chlorine. So magnesium is 3. So I could go on, but I want you to understand. So Na2SO4, how many are these? SO4 is 1 big group ion, and then Na2 is 2, so it's 3. What about aluminum 2SO4 3? Right? How many things are dissolved in it? 2 aluminums and 3 sulfates, so it's 5. So I is the number of particles or number of ions, and we use this here because we need to include that. And then, and this is important, right? The Van Hoff factor for covalent compounds, because covalent compounds, right, are not going to dissolve. So I for covalent compound is 1, right? Because they are not going to dissolve. So for example, what's a covalent compound dissolving in water? Sugar, right? Sugar is C6H12O6. You don't have to know the formula, but sugar is made of carbon, hydrogen, and oxygen. These are all non-metals, so it's a covalent compound. So I for sugar will be 1, whereas I for salt will be 2. Van Hoff factor. A very important concept. So if we go back to our colligative properties list of formulas, right, you realize that these have I in them, right? And this I is the Van Hoff factor. By the way, I don't know if you've seen this. I don't know how many people have done this, but again, if you add salt to water, it's going to freeze. It's going to take longer to freeze, right? And it's going to take longer to freeze, and it's going to take longer to boil. So the freezing point will decrease, and then the boiling point will increase. By how much? Now you know that you can calculate by how much, by giving me I times KB times M. Okay, so that is colligative properties. Very important concept. So I can ask you, This is not 7, is it? Because I think we already gave question 7. So this is question 8. So question 8 is, what are the boiling point, right? Boiling point and freezing point of a 1.96 molar solution of naphthalene. Molar is small m. It's just that this one is this font is all, this is small m, so take this one as molality, right? So what are the boiling point and freezing point of a 1.96 molar solution of naphthalene in benzene, right? When the normal boiling and freezing point for benzene are this, right? So I'm telling you, like, hey, the normal boiling point is this, the normal freezing point is this. If you add this amount of naphthalene, how much is the boiling point and freezing point going to change, right? So you're going to, again, and naphthalene, by the way, I will just give you a hint. Naphthalene is a covalent compound, so I is 1. But you're going to find delta TB, which is the change in boiling point, delta TF, which is the change in freezing point, and then from there you are going to give me the new boiling and freezing point, right? So make sure that you give me that. That's question 8. All right. Then question 9 is, the elemental analysis of organic solid extracted from gum arabic showed that it contained this much carbon, this much hydrogen, this much oxygen. What? Ooh, I know what this is, but let's skip it. You can, don't you do it as a question, you can do it for practice. Because it tells you, like, hey, we found this amount, and then it gives you a freezing point depression, and then you can find the molar mass and molecular formula, right? Why? Because guess what? Just like we discussed earlier, right? Just like we can find the change in freezing point by using molality. Guess what? We can measure the freezing point of something, the change in freezing point, and it will give us the molality, right? So if you know Kf and you know this, you can find the molality, right? So that's what this thing is. It just gave us, right? It just gave us the Kf, it gave us the delta Tf, and then you can find the molality. And then if you have the molality, and then you have this percent of each composition, if you go back to your last class, you can use that to find the molar mass and the molecular formula. It's a fun question that I would do it if I were you. Okay, all right, so let's go to the last colligative property. The last colligative property is osmotic pressure. Right? Osmotic pressure. And you might have heard of osmosis, you might not have, so that's why I wanted to introduce it. Osmosis happens in nature, and then we also use it in the lab a lot. So osmosis is what? It's a selective passage. It's a movement of solvent molecules through a porous membrane. We call it semi-permeable membrane, from a dilute solution to a more concentrated one, right? Everything that I just highlighted is important. It's a selective passage of solvent molecule through a porous membrane from a dilute solution to a more concentrated solution. This can be a fun, definition or multiple choice questions. So make sure that you understand this, right? So this membrane, right, is semi-permeable. Why? Because it only allows solvent molecules through, and then it stops the solutes, right? So if you have that, if you have two, so you have one chamber here, you have another chamber here, right? But then you have a membrane that is semi-permeable, so it can only let through the solvent, right? The solute cannot go through, and then one side is dilute, the other side is more concentrated. So the question is, and the question I can ask you is like, okay, what direction will it take? What direction will the solvent take? And the solvent will go from dilute to more concentrated. Why do we want to do that? We want to do that so that we can equilibrate or balance, right? So the solvent will go from dilute to more concentrated so that we can later get it to balance. It's called osmosis, right? And with osmosis comes osmotic pressure, right? There is a pressure that the osmosis goes through, and this pressure is, but also this has I as well, right? It also depends on I, but the osmotic pressure is equal to I times molarity in molar times R, which is a constant that I'm gonna give you, and then temperature has to be in Kelvin. So this is how you calculate the osmotic pressure, which is the last colligative property, right? So now you understand vapor pressure lowering, boiling point elevation, freezing point depression, osmotic pressure. Be sure to not only understand it, not only know how it changes, whether it goes up or down when we add more things into the solution, but also make sure that you know how to calculate that change. And now you know how to do that as long as you have the concentration. Okay, I hope that makes sense. Now, osmosis doesn't just happen in a beaker, right? It happens in real life as well, right? And when it happens through cell membrane, right? This is a red blood cell, for example, right? So if you take a cell and it's permeable to water molecules, right? To water molecules, what ends up happening is, if you put it, I want you to pay attention. If you put it into the same concentration, if you put it into a solution that has the same concentration inside and outside, it's an isotonic solution. If you put it into an environment, right? An environment in which you have you have less outside, right? Low concentration outside, high concentration inside. It's called an hypotonic solution. Low outside, hypotonic. And then when you have an environment where you have high concentration outside and then low inside, it's called the hypertonic solution, right? And by the way, again, it is not just in cells. It's not just in like beakers. We can see it in cells, even in pickles, man. Like whenever you make pickles, that you use the same. If you put a pickle in salt or high concentration, guess what happens? Water is going to move inside, right? And guess what ends up happening? It swells up. So here you see that if you have a hypotonic reaction, actually, yeah, you put it in a low concentration salt. If you have a hypotonic solution, right, what ends up happening is water goes inside, because through osmosis, we go from low to high concentration. And what ends up happening to the cells is they become bigger. So your red blood cells can actually burst, right? And then if you have the opposite, where you have high salt concentration outside, your cells are going to be hypertonic and they will shrink, right? I've seen this happen. So that's why sometimes actually a lot of water can become too much, by the way, right? A lot of water in blood can become too much just because of that, all right? But let's look at question 9. Question 9 is saying, what is the osmotic pressure of a 3.45 molar aqueous urea solution at 14.5 degrees Celsius? That's an easy one. Question 9, make sure that you work on that, all right? And let me talk about one more thing, and then I will give you question 10, and then we'll be done. And the last thing that I want to talk about is called colloids. Colloids, right? Colloids are kind of weird. They are not really solutions, right? They are dispersion of particles of one substance throughout a dispersing medium of another substance, right? So the problem is that so usually a lot of people confuse colloids with solutions, but colloids are particles are larger than solutes, right? And usually the suspension is not as homogeneous. You can tell, right? If you can see, like, how do I say this? Yeah, like if you can see here, as you see like dust in the air, it's a colloid mixture. You can see it. So it's not a homogeneous mixture, right? It's not a homogeneous mixture. That's why it's not a solution. So more examples: fog, mist, smoke, mayo, jelly. So things that are they don't seem quite dissolved, right? They're just smaller, but they are still much, they are not dissolved at the molecular level. We call them colloids, right? They are kind of mixed, but they are not completely mixed at the molecular level. If you look at them under microscope, you'll see that they are still together, right? We call these colloids, right? And again, colloids sometimes do have, they can be hydrophilic or water loving, or hydrophobic or water fearing, right? So if you have a colloidal particle that loves water, it's going to be exposed to water. And then if you have colloidal particle that doesn't like water, guess what? They're going to kind of be all together or reoriented against water. But you have some of them, like soap, for example. Soap has a hydrophilic head and a hydrophobic tail, where they can reorient to kind of, the hydrophobic or the water heading side to go away from water, and then the water loving sides to be exposed to water. But that's all I'm going to talk about when it comes to colloids. Make sure that you know what they are. Make sure that you can give me examples of colloids. So question 10 is, a bag is made of semi-permeable dialysis tubing and is filled with 0.05 molar potassium nitrate solution and then pressed into a beaker containing pure water, right? And then number 1, will the flow go into the bag or out of the bag, right? And then what will the pressure be? What's the osmotic pressure when you have this temperature, right? So you should know how to answer that. You should definitely know how to answer that based on everything that we have discussed, right? But I think that is a good place to stop. So make sure that you know everything that we discussed, from different types of concentrations, where it is percent by mass, percent by volume, ppm, weight by volume. When it comes to molarity, the mole fraction, we talked about the colligative properties and how to calculate them, but also make sure that you know different definitions, different types of solutions, saturations, and so on and so forth. So this is a good introduction to solutions, and you should be able to understand this and not only understand it but know what is happening at the molecular level, because we did discuss the structure and the polarity and all that stuff. You should know whether something will dissolve into something or not. You should know the effect of temperature. You should know the effects they have on pressure and things like that. So make sure that you understand, because this is one of the most important chapters, especially when it comes to what we do in the lab. When students don't understand this, they get into the lab and they get confused, especially when it comes to calculations. So make sure that you understand, you practice, try to make an effort to remember this. And of course, if you need more help, do not hesitate to reach out. And other than that, guys, I will see you in the next chapter.